Hi everyone, I'm Sasha. I work in the YTsaurus team, and I am a lead developer of SPYT. This is a system that enables using Apache Spark, a well-known framework for distributed computing, along with YTsaurus. Today's webinar will show you how to work with YTsaurus using Apache Spark. First of all, we'll tell you how Spark is currently integrated into YTsaurus and when you should use it. Then, we'll show you how to set up a Spark cluster in YTsaurus. After that, my teammate Alex will run some computing operations on this cluster and explain what you need to know when working with Spark in YTsaurus. Finally, we'll tell you about our plans on further SPYT development. In the YTsaurus ecosystem, SPYT is on the same level as other data computing modules such as YTsaurus, MapReduce, and YTsaurus, which is integration with ClickHouse. As we were developing YTsaurus as a system for storing and processing large amount of data, Spark integration was a logical move. Since Spark provides a platform-agnostic engine to run complex queries over large structured and non-structured data using distributed computing. The Spark engine is independent of both data storage and managing computing resources. This is why we can use it with any storage and computing platform configuration. For instance, initially, Spark was intended to launch against the data within the Hadoop file system, HDFs, and used Yarn, a Hadoop resource manager. However, you can also use Spark to process data stored on an S-compatible storage with Kubernetes as a resource manager. In YTsaurus, we have both a data storing system and a computing resource manager, which means the Spark engine integration allows us to build quite complex data processing workflows within YTsaurus. Now, a few words on when to efficiently use Spark in YTsaurus. First things first, SPYT is good for developing complex pipelines, especially those with join and group operations. This is because Spark stores the intermediate data in the RAM. This significantly speeds up data processing because, unlike conventional MapReduce, you don't need to write data to disk and then read it again. Well, Spark is also efficient for building integration ETL pipelines from other systems. This is because there are many connectors for various data storage systems, both relational and non-relational, that work with Spark. Well, you can use them as data source, create an information process, and write the result to YTsaurus. Well, additionally, Spark is very good for ad hoc analytics against large data, since it has such convenient tools as Spark Shell. It can also be easily integrated with Jupyter notebooks, which enables, say, caching certain intermediate results in the RAM and running various queries over them. We do not recommend using Spark in YTsaurus in two cases. First, when the size of the data being processed in a single transaction is greater than 10 terabytes. This is because it also increases the size of intermediate data, and once there is no room for it in the RAM, it starts being spilled to the disk, which significantly deteriorates the performance. This is why Spark is no longer efficient when it comes to such large data. Well, the second case is when the processing comes down to single map or MapReduce operations. For those, we at YTsaurus have other operation types such as map and MapReduce, as well as intermediate sorting. Well, now let me tell you how you can set up a Spark cluster within YTsaurus. Basically, we use a standalone Spark cluster, which is part of the common Spark distribution, and deploy it inside a YTsaurus cluster. We do it through a vanilla operation. Vanilla is a type of operation that enables starting a certain distributed process in YTsaurus. After describing a few types of jobs and specifying the number of jobs you need for each type. So, to deploy a Spark cluster, we need to describe 4 task types. The first one is Spark Master that manages all processes within a Spark cluster. Well, then, a few Spark workers that actually do the data processing job and work with the data store, which, in YTsaurus, is called SPYT. Well, there are also 2 optional components. The first one is History Server that is also included in the common Spark distribution. It enables storing operation history, which may be handy for troubleshooting and issue analysis. The second one is Apache Livy that we added recently. It provides a convenient ATP interface to work with Spark through ATP. This means you can just send queries there and get the result as if working with a regular SQL engine. We will show you how it works later in our demo. Well, so once we start a vanilla operation in a YTsaurus cluster, the scheduler allocates the appropriate resources directly on the executor nodes. The executor nodes are those that manage the computing. They have a certain amount of resources, that is, a certain number of cores, and an amount of RAM. And a part of those resources is reserved for the Spark cluster. Such nodes run the relevant JVM processes that, together, form a standalone Spark cluster. Well, to set up a Spark cluster, we need to write its configuration to Cypress to a certain path that is called discovery_path. It is created once the cluster starts and receives the global configuration that can be read by all components and is used to enable communication across all components. Now, a few words on Spark versions that are compatible with YTsaurus. Currently, we are using a fork based on Spark 3.2. Well, let me clarify right away why we are using a fork. Initially, when we were adding the support for Spark, we needed some features the Spark core didn't have. For instance, Spark scripts in the cluster mode in a standalone cluster or IPv6 support. At the development stage, this was acceptable. However, when we went open source, we realized such a solution leads to various limitations for the users. This is why we want to discontinue the fork moving forward and enable SPYT support for various core versions of Spark. Well, if you go to our GitHub repository, you will see everything related to the Spark integration in the /Spark subdirectory. In its turn, it has 3 subdirectories. The first one it called patches. This is just a list of Git patches that, when applied one by one to 3.2 from the main Spark repository, will lead to the version we are currently using in our fork. Well, the fork is in the it/Spark/Spark directory and is built into a Python module called YTsaurus Spark. Everything related to SPYT is in Spark over it. Also, SPYT has a few artifacts for Python and JVM, the Python artifact is the YTsaurus SPYT Python module. That depends directly on YTsaurus Spark. First, it includes the API for writing apps that can be used in applied scripts. Second, it has a few command line utilities. Some of them, such as Spark Submitit and Spark Shellit, are shells for common PySpark utilities. Well, others are used to work with a cluster inside YTsaurus. For instance, Spark Launchit starts a Spark cluster within a YTsaurus vanilla operation. While Spark Discovery it shows information on an existing Spark cluster, that is, we provide it with discovery_path as input, and it visualizes the info. We will show how it works a bit later. There are also some JVM artifacts. The first one is the SparkIt data source module. This is a library deployed in the Maven central repository. Basically, you can install dependencies over it and use it in your apps if you use Java or Scala for Spark. There are also modules for working with the YTsaurus file system and those for managing task runs. Well, so all these Java artifacts are built along with our fork and for a so-called build that should be pre-deployed on a YTsaurus cluster. This is the server runtime environment. All these modules will be on the class path of all Spark components, that is, on the cluster side. Well, also, we have two YTsaurus client modules to work with YTsaurus. For Java, YTsaurus client is automatically retrieved through dependencies. Well, for Python version, we just need to install YTsaurus client somewhere nearby so that YTsaurus SPYT could use it. I mean, if we just install YTsaurus SPYT without installing the client, the system will check whether a client of a certain version is installed, and this check will fail. Alright, this concludes our formal part. Now we will show you how to set up a Spark cluster in YTsaurus. For a cluster to work with SPYT, it must have a SPYT distribution pre-installed, right as I showed here. That is actually a build with the Spark fork and our SPYT libraries. If you are deploying a cluster in Kubernetes using our operator, you need to add a separate section to the manifest that specifies the Docker image with the required SPYT version. For an example, you can see our operator repository. Here, we can see we are using SPYT 1.72.0. Well, you can also find all SPYT Docker image versions on Docker Hub. Here they are, filtered by YTsaurus/SPYT. Alright, so we have a cluster set up in Kubernetes that we pre-configured using our operator. Let's go to it and try to set up a cluster based on it using a vanilla operation. Well, to start the cluster, you need to use the command line utilities that are part of the YTsaurus SPYT package. These utilities work with Python 3.7 or higher. Actually, we recommend creating a dedicated virtual environment where you will then install YTsaurus SPYT and YTsaurus client. Let's do it now. So we are creating a virtual environment. We are activating it. and install YTsaurus client and YTsaurus SPYT, since YTsaurus client is not part of the YTsaurus SPYT dependencies. So, YTsaurus SPYT got installed, and we also have YTsaurus Spark, the one I mentioned before. Now let's create discovery_path, where we will store the configuration of our cluster that will start inside YTsaurus. We will just create a so-called map node. Technically, it is the same as a directory, it's just called a map node in the Cypress terms. Great! We created it. All right, we're all set to start the Spark cluster. For this, we will use the Spark Launchit utility. It has a few properties I'm going to tell you about. The first one is discovery_path we've just created. We can just copy it. Then, we need to specify a pool in YTsaurus scheduler that will determine how much resources we can use for our cluster. Let's pick the research pool. Well, in addition, we need to specify the amount of resources allocated to all Spark components. That is, to the master, workers, history server, and Livy server. First, however, we need to make sure we have enough resources. Let's go to the system page. We can see we've got 55 cores and around 40 gigabytes of RAM available. This is well enough to run a cluster that will work. Let me tell you about minimum requirements. The minimum requirements are 4 cores, as we need 2 for the master and 2 more for the workers. Out of these 2, one goes to the app driver process and the other to the executor. This makes 4 cores in total. There cannot be fewer than that. Well, so let's create 4 workers. And provide each with 4 cores. And 4 gigabytes of RAM. We also need to allocate some RAM to the container where we will run workers. In the YTsaurus terms, this is called a job. So, the RAM allocated to the container for workers is made up of the worker's RAM, 4 gigabytes. This value is provided to the XMSTVM property. That is, this is the RAM that XMSTVM can use directly. We also need to allocate some additional memory that is set through the worker memory overhead property. By default, it equals 4 gigabytes, but we'll reduce it to 1. In fact, we do not need 4 times 4, that is, 16 gigabytes, that will just be idle. Well, finally, we have an interesting property called TMPFs. This is the size of the file system in the RAM that, historically, is 150 gigabytes by default. Well, for clusters launched based on Kubernetes, this is too much and may cause issues, but this is just so. This is why we should either explicitly reduce the TMPF size or just disable it. Actually, we don't need it now, so we'll disable it. Generally, however, the amount of memory allocated to a container for a worker is made up of worker memory. worker memory overhead, and TMPFs. Then, it's multiplied by the number of workers. So, let's disable TMPFs. We should note that our cluster is running in Kubernetes. For it to become available for our local machine, that is outside the Kubernetes cluster. The latter has so-called TCP proxies. These proxies use the node port feature to provide access to the cluster through certain ports that are open on any cluster node. Such port range for node port generally starts with 30,000. In our case, however, we start from 32,000. And we need to specify that as well. First, we enable it. Enable TCP proxy. And then specify the port range, TCP proxy range start. $32,000. We don't need history server either, so we'll disable it too. Well, if we did launch a history server, most likely, we would also need to explicitly specify the number of cores. By default, history server requires as many as 8 cores, which is often too many. Well, we will also enable Livy because we'll need it further in our demo. Well, looks like we're done. Let's start the cluster. Alright, yeah, I mistyped the command. Let's run it once again. And enable Livy again as well. So, let's start the cluster. We can see we've got 6 jobs running, out of which 4 are workers. That we specified, another one is master, and yet another one, Livy. Let's look at the Operations tab in YTsaurus. We can see it's up and running. We can also go to the Spark cluster web UI. Here we can also see the cluster is up. Finally, we can see that now we have. Right, we used 23 cores, and the RAM consumption also increased. Well. Okay, now let me show you the command that allows you to view the cluster info. It is Spark Discovery It. The only property it may have is discovery path. It will list all endpoints for web UI and for communication between the master and workers. There's also REST API. And there's a link to the operations in the YTsaurus UI that we just viewed. Let's now run a task on this cluster. I've got a small dataset. It is in the input_data table. It includes some basic IDs and UIDs. Well. And there's also a small Scala app. It creates a Spark session and reads the table where we provide the first argument. Then, the ID gets the remainder of the division by 10, groups the result by remainders, calculates the accounts by each remainder, and delivers the result to the address we provide as the second argument. So, it's a basic project with a single class and only one main method. Well, to build this project, we need to create a manifest in any build tool, such as Maven, Gradle, SPYT, or whatever, and add 3 dependencies to it. Namely, 2 Spark dependencies, SparkCore and SparkSQL for 3.2.2, since our fork is based on 3.2.2. The third one is SPYT, any of the most recent versions. All dependencies are provided because we already have them pre-installed on the cluster and don't need to include them in the app distribution. Let's build our project. SPYT clean package. We've got the file we'll upload to the Cypress. So we take our jar file and write it to the Cypress. Now we can run it. Let's do it using the Spark submit-it shell. It has the same properties as the regular Spark submit. Well, it has discovery path that points to the cluster where everything should be run. Well, for deploy mode, we set cluster, then we specify the class where our logic is implemented and the path to the jar file we packed it into. So, here is our input_data table on the Cypress. Here it is. And we also provide the path to the grouping_result table since we have grouping. Okay, let's run it. As we can see, we launched an app based on a Spark cluster. It ran quickly since the data amount is quite small. The app stopped successfully with the finished status. Now let's check we've got the output data in the directory we specified as the second argument. Let's go to the Cypress. We can see the grouping_result table is there. Let's open it. Right, we've got 2 columns we were running the grouping by. The first one is ID_mod_10, which is the remainder of division by 10. And it has the values from 0 to 9. The second one is for the remainder counts. So, everything worked out as expected. This concludes my part of this webinar. I'm turning the floor over to Alex, who will show you more ways to work with YTsaurus using Apache Spark. Hi everyone. I'm Alex and I work in the SPYT team. Today, we'll look at some hands-on examples of using SPYT in a more in-depth way. I'll be acting as a data engineer of an assumed pet store. I will be using Jupyter Notebook, writing Scala code in Spark shell, creating a Python job, and leveraging Query Tracker. Here's our plan. First, we'll create some test data. Then, we'll write it into YTsaurus and process it. For starters, we'll connect pandas and certain system libraries. After that, we'll create a table with users. Each user will have an ID, name, city, and age. This data will be pseudorandom. For each user, we will determine a list of their pets, also in a pseudorandom way. Then, our shop will have a table with orders. Each order will have an ID, time, user who submitted it, and the amount. This concludes data preparation. Now, we have the following questions to answer. How many pets does each user have? How are the user's age and their spending related? And what is the most popular name among our users' pets? Finally, we'll have an additional task. We will create a Python job to run a script that will update our user's age. For starters, let's connect the SPYT library, determine the proxy in the YTsaurus cluster we are connecting to, and specify the discovery_path of the cluster we previously launched. Then, we'll run the connect operation. In the connect operation, we need to specify discovery_path and some additional properties. In particular, I will need to provide each executor with a CPU and 2 GB of RAM. If we go now to Web UI, we'll see our application running and waiting for our commands. Let's move to writing data to YTsaurus. First, let's convert Pandas data frame into Spark data frame, which we will then write. We will define that all data is sorted by the ID column and all keys are unique. We'll select scan as the storage format, as it is the most efficient in terms of compressing and visualizing data. Let's specify the output table. Then we'll run our write and wait a bit. Our write has been completed. After opening the respective folder, we'll see our newly written table consisting of 500 rows. Then, let's assume there is a new user in our system. Our table is static, but we still can write additional data to it. This user's name is Max and his ID is 500. Since this ID is larger than all previous ones, the sorting conditions and the key uniqueness still work. So we can just write this record in the append mode into our existing table. Let's go to the end of our table, and here's our new user. Alright, now we need to write the table with pets. I will use this example to show you how to work with transactions. First, we'll create a client to connect to YTsaurus, and then run a new transaction in this cell. Then, we'll convert Pandas data frame into Spark data frame and write data under the transaction we created, by specifying it in the write_transaction property. We will also connect type_v3 since we are writing data of a complex type, namely arrays, and we'll specify the output table. If we go to the UI now, we'll see the table was not written. This is because we did not commit the transaction. So let's commit it, and now we can see the new table in the UI. Finally, we need one more table, the one with orders. Since orders come frequently, it is feasible to use a dynamic table to store them. There are some specifics when it comes to working with dynamic tables. We need to define the data schema, then create a table based on that schema using YTsaurus client, specify that it is dynamic, and mount it. Now in the UI, we can see a newly created empty table. Let's write our data to it. Transactions also have certain specifics. In particular, it might happen so that our calculation stops working. In this case, the system will write certain intermediate data. We need to explicitly confirm we are ready for such a scenario. For that, we set this option to true and write additional data to the table. We can see the new data. This concludes writing. Now let's solve our tasks. The first question was how many pets each user has. To answer this question, we need two tables, the one with users and the one with pets. We'll read them under a single transaction. When reading the table with pets, we'll specify that it has data of complex types. Then, we'll join these two tables by user_ID. After that, we'll take the array size to see the amount and select the required columns. Finally, we'll output them. Everything got calculated correctly, just as planned. We successfully solved our first task. This concludes our work with the Jupyter Notebook. So, we need to terminate our Spark session. If we go to Web UI after that, we'll see the session has been terminated and we have some free resources available for other calculations. Let's look at our task list again. The next question is how the user's age and their spending are related. To answer it, let's go to Query Tracker. Let's select the SPYT engine and put there the SQL query we prepared beforehand. We are reading the static table with users and the dynamic one with orders. Since dynamic tables have versions and timestamps, we need to specify that we will read the latest available data. Now we'll join this data by user_ID, group it, and sort by age. For each age, we'll output the average spending. To specify the cluster that will handle this query, we need to type discovery path into the settings field. Let's run the query and wait until it finishes. If we go now to Web UI, we'll see there is an application running. Let's wait until it's over. Now we can analyze the data we got. If we do it carefully, we will notice that the older the user is, the more they spend on their pets. We'll have our last question still unanswered. What is the most popular name among our users' pets? We'll solve this task using Spark shell. First, we'll run the command to connect to the shell. Here, we specified discovery_path and the settings regarding the executors we need, just in the same way we did it for Python. We'll be writing Scala code, and Spark will create the required environment for us. Let's connect a library with SPYT and read the table with all pets. We'll also specify type_v3 here. So, we read a table with user_ID as a number and the list of pets as an array. Let's make a data frame out of it, where we'll have a row with a user and another one with their pet. Then, we'll calculate the aggregate data, group it by pet name, and count the number of times the pet is mentioned in our table. We'll write the result to the pet_stats table and open it to see the statistics. Now let's move to our additional task, which is a script that updates the user age. The script is on the YTsaurus cluster. We are connecting SPYT and then the function we need from the PySpark package. We've got two input arguments, which are the input and output tables. Let's start a Spark session and output the logs so that we could analyze the issues quickly, if there are any. We'll read the table with users, add one to the age row, and write the result to the output table. Let's quit Spark shell and start the job with this command. Same as with running Java code, we put cluster for deploy mode, then specify the address of the executable code, as well as the input and output tables. Let's run it. In WebUI, we can see the driver and the relevant application starting. The calculation is being processed. And it's over. Let's go to our folder to see a new table with the age increased by 1. This concludes my part of the demo. Thanks for watching. I'm turning the floor back over to Sasha. Alright Alex, thanks for your demo. In conclusion, I'd like to show you how to stop a Spark cluster in YTsaurus when you no longer need it. I'll also briefly share our plans on further SPYT development. Stopping a cluster is quite easy. Go to the operation page. It has a button that says complete. You can also find this button in the operation list. Well, click complete to stop the operation. Now go to the resource page. You can see the resources are still busy, but the scheduler will release them soon. Here we go, the resources have been released. We got back to the state we had before launching the cluster. The CUS and RAM may now be used again for other tasks. Finally, a few words about our plans for the future. As I said, we are working on discontinuing the Spark fork so that our users could use versions other than 3.2. Moving forward, we are planning to enable support for a few latest major Spark versions, starting from 3.2. This will enable our users to choose a version that suits them and migrate the existing Spark pipelines from other platforms to YTsaurus. We also want to enable integration with Scheduler, the tool our teammate Jaeger told you about in one of the previous webinars. We want to enable running a job directly in YTsaurus without creating a standalone Spark cluster through a vanilla operation. This will allow for more flexibility when managing the resources in a cluster. Additionally, you won't have to maintain a live Spark cluster in a separate operation while it is idle. Well, finally, we want to add structured streaming support based on SPYT. This will enable storing the intermediate state in dynamic tables, rather than in ROXT, which is offered by default, or files within the file system. As Ivan, our teammate, mentioned in one of the previous webinars, YTsaurus dynamic tables can be used as a key-value storage. This will allow us to use what YTsaurus has by default, rather than add new components. This concludes our webinar. Thanks everyone for watching.